Welcome back to C++ Under the Microscope. Today we are doing a complete breakdown of std vector pushback versus emplaceback. We will look at what the standard says on CPP reference, then examine the generated assembly on Godbolt for a variety of examples. By the end, you'll know exactly when and why to use each one. Let's start with pushback. Here on CPP reference, we see two overloads. The first takes a const L value reference. It copies the element. The second takes an R value reference. It moves the element. In both cases, you are passing an already constructed object type T. Now let's check emplaceback. It's a variadic template. It takes a forwarding reference pack and forwards those arguments directly to the constructor of T. The object is constructed in place at the memory location allocated by the vector. No temporary T is ever created. The complexity is the same, amortized constant for emplaceback and the same for pushback. Amortized constant time is a way of measuring the cost of operations in a sequence. It means that while a single operation may occasionally be expensive, the average cost over many operations is constant. The classic example is appending to a dynamic array. Most appends are instant, but when the array is full, it must double its space and copy everything. That one operation is costly. However, because it happens so rarely, the average time per append is still constant. Here is the simplest case, a vector of strings. And we push a string literal. Let's compile this with Quank. No optimizations, as we can see. Look at the call instructions. First, we see a call to the string constructor. This is the constructor for the temporary string built from our literal. This here is our literal. Hello world. Then immediately after, we see a call to the move constructor. Here is it. That moves the temporary into the vector's storage. And finally, a call to the destructor for the temporary. Here it is. So for single pushback, we get temporary construction, move, and destruction. 3 operations. Now replace it with emplaceback, same arguments, and recompile. There is only one constructor call, the same string constructor as with pushback. Here it is. But this time it's constructing directly into the vector's memory. So no move, no temporary destruction, one operation. In the pushback case, the compiler must create temporary because that's what the function signature requires. It takes a string. In emplaceback, we are forwarding the literal directly to the string constructor inside the vector. Now let's look at a more complex type. std pair int string. With pushback, we use braced initializer. What does that do? We will see a call to the std pair constructor. Here, that's the temporary pair. Then a move constructor for a pair. Here it is. Moving it into the vector. Then a destructor for the temporary. It's basically the same pattern. Now let's change it to emplaceback. Emplaceback with integer 1 and our string literal. 2 arguments. They are forwarded directly to the pair constructor. Here is that call. Only one pair constructor call. Inside that constructor, the string is constructed from the literal and the int is copied. Everything is built in place. This is where emplaceback really shines with multiple arguments. Pushback would require you to create a temporary pair yourself or use list-initialization, which still creates a temporary. A common misconception: can we do this? This does not work. Emplaceback uses perfect forwarding, and brace initializers cannot be deduced by the template argument deduction. The compiler cannot figure out what one and hello world should become a std pair of int and std string. Pushback works because it's not a template in the argument. It takes a concrete pair type. The brace initializer is used to construct a temporary pair, which is then passed to pushback. So if you want to use list initialization syntax, you need pushback. Let's look at move-only types like unique pattern. With pushback, we explicitly move the pointer into the vector. This works fine. We see the move constructor for unique pattern being called. Now let's change it for emplaceback. With emplaceback, we can construct the unique pattern directly in place. One constructor call for unique pattern right in the vector's memory. No separate move. This is slightly more efficient and can be cleaner if you don't need the pointer elsewhere. Here is an important subtlety: explicit constructors. S has an explicit constructor from int. Pushback 1 would fail because pushback needs to convert 1 to an S to create the temporary. But explicit constructors disable implicit conversions. The error says no matching member function for code pushback. Emplaceback uses direct initialization inside the vector, so it can call explicit constructors. This is a deliberate difference. If you have explicit constructors, emplaceback may be your only option for in-place construction. Before C++20, aggregates like point had no user-declared constructors, so you couldn't use emplaceback with multiple arguments. Pushback with list initialization was the only way. As you can see, with C++17, that does not compile, and it gives some reason for that. If we change that to C++20, it compiles fine. C++ changed the rules. Aggregates can now be initialized directly with parentheses, so emplaceback works. But this is compiler dependent and you need C++20 enabled. So based on everything we've seen, here is a practical guide. Use pushback when you already have an object of type T. You want to use list initialization syntax, this one. You need to be explicit about copying versus moving. And use emplaceback when you're constructing the element from multiple arguments. You want to avoid a temporary or non-trivial types. You need to call the explicit constructor. You're dealing with move-only types and want to construct in place. Also remember, emplaceback can sometimes lead to longer compile times because it's a template. That covers everything from the assembly differences to the edge cases. Pushback and emplaceback are both useful tools. Knowing what they do under the hood lets you choose the right one for the job. Thanks for watching. In the next episode, we will look at another C++ feature under the microscope. If you have requests, leave them in the comments. See you next time. Until then, keep exploring.